All right, this is Mr. Gillum, and today what we're going to learn is about the angle bisector theorem and its converse. Angle bisector theorem and its converse, and we're going to learn how to bisect an angle tomorrow. But we're also going to do a little reviewing on the Pythagorean theorem. I noticed that some of you maybe don't remember it very well from last year, but it's going to come in really handy for all these perpendicular lines we've been making. So there's that. Now, the angle bisector theorem says if you have a point on the angle bisector, then it is equidistant from, the perpendicular distance is equidistant from each side. So if I have a point right here, if I have a point right here, this guy, that perpendicular distance is equal to that perpendicular distance. Or if I have a point way out here, this perpendicular distance is equal to this perpendicular distance. Okay, and that's all assuming that this line right here makes these two angles equal. Okay, so as long as these two angles are equal and this bisects that angle, perpendicular distance from any point on there will be equal. Okay, that's what the angle bisector theorem is saying. All right, so the converse says if you notice that you have a point somewhere, say like right here, where its perpendicular distance happens to be exactly the same, then you know it must lie on the perpendicular, sorry, not the angle bisector. All right, so if you know a point and it's equal distance from there to there, its perpendicular distance is exactly the same, then you know it must lie on the angle bisector. Okay, so this is another one of those that works forwards and backwards. It's the angle bisector theorem, and its converse says if you're on it, you must be a perpendicular distance, equal perpendicular distance away from each of the sides of the angles. All right, so there's that theorem, and it's pretty straightforward. And we might use it with proofs here a little bit, but the big chunk of the day, what we need to spend time on is the Pythagorean theorem. All right, and the Pythagorean theorem classically is known as a squared plus b squared equals c squared, but it does matter which variable you choose for a, b, and c, which side of your triangle. Okay, I must make sure that I tell you this right. Triangles only. Okay, right triangles only. This only works for right triangles. And basically it's a relationship between the sides of a right triangle. Okay? All this stuff I could tell you about right triangles that you need to know, or triangles in general. Let's start with what I hope you already know, but you might not already know. The hypotenuse of a triangle is the longest side. Okay, and is represented by the variable c. Okay, so in fact what I'm going to do is I'm going to change this equation to leg squared plus leg squared equals the hypotenuse squared. Okay, that is the relationship of Pythagoras, his theorem. And to find the hypotenuse on any triangle, not just a right triangle, it's always across from the biggest angle. Okay, but in a right triangle specifically, always it's across from the 90-degree angle, because 90 degrees is at least half of the total measure of the triangle. 90 must be the biggest measure. That being said, if it was an obtuse triangle, the longest side would be across from the obtuse angle. If it's an acute triangle, whatever acute triangle or acute angle there is across from that, the biggest acute angle will be the biggest side. Okay, that's just a general rule for all triangles. Okay, however, the Pythagorean theorem, only right triangle. Now we're doing a lot of perpendicular bisectors. We're doing some angle bisectors with perpendicular distances. So you can see where this is going to come in really handy because we're making a lot of triangles. See if I see a triangle right here when I drew that perpendicular distance in. I see one right here. I see one right here. So you can see this Pythagorean theorem is going to come in really handy for us. All right, and basically the relationship is you take the leg squared plus the leg squared, and you know it must equal the hypotenuse squared. Every time, no matter what, for all right triangles, it'll always work. Okay, so it's used for finding the distance or the length of the side of a right triangle. Only a right triangle though. All right, and now Pythagoras noticed this relationship way back in the day. He's pretty happy about it. Basically, he had a right triangle, and he might not have done it this way, but this is one of the proofs of the Pythagorean theorem. And he said, okay, I got this triangle, leg and hypotenuse. And I know there has to be a relationship here somewhere, so I just got to find it. And so what he did was he decided, okay, let's just pretend that let's just add on right here. Let's just say I had a rectangle that was an A by A rectangle, an A by A rectangle. Okay, and then its area obviously would be A squared, and in this case it would be A squared. And then we have a B by B, or a leg by leg again, and we'll just call him B squared. And you know what, I'm going to take a step back here for a second. Let's just put some numbers with this. I think it might make a little more sense. Let's just say this guy's a 3, this guy's a 4, and this guy's a 5. And this is a perfect right triangle, and I know this is going to work specifically because I've done the math already. But if this was 3, if I squared the 3, I would know that it is a 9, an area of 9. And if I squared the 4, I would know the area is 16. If I square the area of 5 by 5, or if I just take 5 squared, it's 25. Now, what is the relationship between these squared side lengths? What I notice is I have 9 square units plus another 16 square units, and my c squared side, my longest side, my hypotenuse, if I squared its length, I have 25. And I know 9 plus 16 is 25, so he tried a bunch of them. Or whoever, they tried a bunch of them, or you know what, they proved it. They proved it, and there's a lot of different ways of sliding the shapes and making them all work and things like that. But for the sake of review, Pythagoras decided that there was this relationship that if you square each length of the leg, it will add up to the length of the hypotenuse squared. And that is the relationship. I will mention a few other things that might come in handy. There is a special, we call it Pythagorean triple, 3, 4, 5. Leg, hypotenuse. Any multiple of that is also a Pythagorean triple. So 6, 8, 10, 9, 12, 15. We could do 12, 16, 20, 15. Oh, be 15, 20, 25. Okay, and so we have all these different ways that you could have this Pythagorean triple, this exact relationship. 6 squared plus 8 squared is 36 plus 64. That equals 10 squared, 100. 9 squared plus 12 squared is 81. Plus 144 is 225, which is also 15 squared. And so this list goes on forever of these Pythagorean triples. So if you notice 2 legs are 3 and 4, or you notice a leg is 3 and the hypotenuse is 5 on a right triangle, you know automatically what the right or the remaining leg would be. So just something to keep in mind, and just a refresher. I don't have time for a whole lesson on this, even though we could go on and on and on and on about it. There's also another one, 5, 12, 13. If you notice that you see those multiples of 5, 12, and 13 in a right triangle, it may help you to get a shortcut quickly. But like I said, once again, we're not spending 3 days learning about the perfect Pythagorean triples here. Hopefully that was introduced to you previously. But we can spend a little time just practicing the Pythagorean theorem. I do think that's important. So what we're going to do is we're going to find the missing side. So in this case, I'm looking for this hypotenuse over here across from the right angle. I know this is the hypotenuse, and the 2 shorter sides are legs. And because we know that addition is commutative, if I'm using the equation leg squared plus leg squared equals the hypotenuse squared, or I'm going to abbreviate it as a squared plus b squared, where a and b are legs, and c squared, where c represents the hypotenuse, then I know that 9 squared plus 12 squared must equal c squared. And now I have an equation that I can solve. I'm going to actually put this in parentheses here out of habit. I'm going to say 81 plus 144 equals c squared. And so c squared equals 225. And to remove the squared, we're going to take the square root of both sides. I'm going to say c equals 15. So therefore, if c, or the x value, is 15. And since there's no labels, we would just, if we were labeling, we would say units, 15 units. Okay. However, we do need to be careful on the Pythagorean theorem, because it's very easy to get caught up in this simple, take the 2 parts that you know squared and find the last one. What we do need to do is we need to make sure that we know which part is the hypotenuse. So in this case, across from the biggest angle, or the 90-degree angle, we know that 21 is the hypotenuse. So this represents an A, this represents B, or vice versa, and this represents C. So we're going to say x squared plus 8 squared equals 21 squared. So x squared plus 64 equals, let's do it the old-fashioned way. $441. And when I'm solving this, I'm going to go ahead and subtract 64 from both sides. X squared equals, borrow 10 from there, make that 11, 7, borrow 100 from him, give it 10 tens, 7, 377. And I'm going to go ahead and square root this guy right here. And I'm going to say x equals plus or minus the square root of 377. And I happen to know that that's 13 times 19. If I were to reduce it, and unfortunately that there is nothing to reduce there. I have no pairs to pull out. I know that 13 is a prime, 19 is a prime. There's no way for me to simplify that square root. And as I'm solving this equation, I knew it would have two solutions. However, because I'm talking about distance, I know that I don't need the negative part. So I'm just going to say that my length is the square root of 377. And that's the exact length, not an estimated length. Certain parts of your homework will say round, but the exact length would be the square root of 377. It's a rational number, but that's okay. Let's look at another one here. Once again, we need to make sure we know which variable we're solving for if we're finding the hypotenuse or a leg. And in this case, this guy over here is going to represent C, 30. This would be an A value and a B value, or vice versa. And this would be a C value. A and B, once again, represent legs. And so we're going to say x squared plus 24 squared equals 30 squared. And once again, it's just a matter of solving for your unknown, your variable. And 24 times 24. Let's see here. What is that? I believe it's 596. Let's just find out here. $576. Okay. Hope that's right. 576 equals 900. And once I'm solving, I'm subtracting. And I know x squared must equal, see here, 24, 324. And then finally, I'm going to take the square root of both sides, plus or minus 18. However, because we are dealing with distance, I know for a fact that I don't need the negative side. So I'm going to say this distance is 18. Now, I noticed right away that this was a perfect Pythagorean triple because I know that 30 and 24 are multiples of 5 and 4. I know that 5 times 6 is 30, and 4 times 6 is 24, so I know that 3 times 6 would equal 18. So I was talking about those Pythagorean triples earlier. What do we do here? Oh. The next one would be 18, 24, 30. I just didn't go far enough. Okay, there we go. So yes, and also I would like to just do a quick review here on this 324. If you don't know your perfect squares very well, you can always do a factor tree, and you may have to do this on some of your problems. I know that 18 times 18 is 324, but however, if you didn't know that, you could do like 2 times 162 or whatever you want to do. It doesn't matter what number you choose, but its prime factorization will be the same no matter what. And I'm just going to circle my primes here. And I know that 3 times 3 times 3 times 3 times 2 times 2 is going to equal 324. Believe it or not, 3 times 3, 9 times 3, 27 times 3, 81 times 2 is 162, and then times 2 is 324. So these numbers, if I multiply them together, these prime numbers, I know it'll equal 324. And I know that 3 times 3 is 9, and since this is all underneath, umbrellaed by the square root sign here, I know that 3 times 3 is 9. The square root of 9 is 3. I know that I can take a 3 outside the square root sign. That leaves me with 2 times 3 times 3 times 2. And I know that 2 times 2 is 4. The square root of 4 is 2. And so basically for every pair, I can pull that number out. And so finally, there's no prime numbers left underneath here. I just have 3 times 2 times 3. 3 times 2 is 6, times 3 is 18. All right. So if there was some numbers left in, they would have to stay inside the square root. But I'm sure that you've done that before in your past experiences.